So, talking about 10 years, I wasn't really sure exactly what to do. So, at the risk of boring you all, I thought it would be amusing, at least, to look back and see where LLVM came from and how it came to be, and maybe apologize for a few things along the way. So, let's look back and see where it started. Actually, the earliest traces of LLVM start way, way, way back in my first compiler project. I was a enthusiastic little undergraduate. I took a really good compilers class from Dr. Stephen Vegdahl. He's a great professor that had a particular interest in compilers. We went kind of above and beyond the basic compiler class and decided to implement a real x86 code generator. And it was actually a pretty cool thing, looking back on it. It compiled this Tiger language that Andrew Appel was excited about and wrote some books about, all the way down to x86 assembly language. It had a full garbage collector and runtime, something that LLVM doesn't even have yet, is accurate stack scanning and copying GC. Maybe the most interesting part of it, though, is that it had a full IR. And it's terrible in many ways, but this was really kind of the start of where LLVM came from in a lot of ways. And if you look back at this, and I don't expect you guys to memorize this, it had a first-class text format and a binary format. That sounds familiar. It has 3 address code and basic low-level operations like compares. It had an unlimited register file, although at that time Vikram hadn't taught me about SSA, so did not exist quite yet. Had functions, had control flow, and it actually had a lot that was very similar. On the other hand, it was also different. There's no type system. Everything was very simple, and parsing this thing was a real pain, which led me to realize that leading opcodes were really the right way to go. And this was a great project. I learned a lot. And it's always good to have one to throw away, let's just say. So I graduated from school, went to work, did some soul searching, interviewed a couple different places. Vikram tricked me into going to the University of Illinois. Started working for him. We worked on a few projects. And we were talking about lots of different things in the space of compilers. We were looking at simulators. We were working at, he had this really deep enthusiasm for lifelong program optimization and doing multi-stage optimization and compilation. And we were talking about this at one time, and there was kind of this spark where we said, we were looking at what existed, and at the time, in 2000, Java was a pretty big deal. And we said, hey, wow, look, JVMs do all of their optimization and all their analysis at runtime. Well, this is the source of much of Java's power, but it also leads to some problems. For example, the startup time of many Java applications is very slow. What if we could do more optimization earlier? So we could do it in install time of the application or some other time, and then let the JIT do what it's really good at, which is the runtime re-optimization using dynamic information to get good performance. And we were really interested in this, but we looked at it and said, the major problem is that Java bytecode is just not the right representation for this, because it enforces memory safety. It doesn't have a type system that allows you to do strength reduction or other very low-level optimizations, at least not in a really very general way. And so, we were talking about this at one point, and it's like, hey, wouldn't it be great if we had some kind of lower-level virtual machine to optimize Java, and then we could optimize better, and the JIT compiler could do what JITs are really good at. And I don't know about you, but this sounds like it might be a good idea, even though we never got around to building a Java compiler. So we had this discussion in kind of late fall leading into winter, and then I went off to winter break. And one of the best things about school is that you get a full month off for winter break, which is something I miss, let's just say. But the best thing about, so I get restless, as you probably have noticed, and I end up hacking on things when I do that, and so I started working at LLVM. I came back from winter break, and I showed Vikram, and I said, hey, look, here's some cool ideas. And so I went and found a really old tarball, which I put on the web, if you're really that morbidly curious. And it was actually kind of an interesting thing. And so here I want to talk about what existed in LLVM as of 1 month old. And it wasn't big. It was only about 10,000 lines of code or something. But it's actually fairly interesting in how similar it is to today's LLVM. it had the AS, the DIS, and the opt tools. Right? Now, 2 of those got renamed, but those allowed round tripping of the LLVM IR at the time, and that allowed full textual, full binary representation, and all that kind of stuff existed very early on. And we were talking about optimization, so I was pretty excited about that and did some very simple things and implemented a really brain-dead did code elimination and constant propagation passes. And it was starting to become interesting. Now, one of the funny things about it is it's actually remarkably similar to what we have. So the directory structure, for example, was already there with the lib and tools and include LLVM, and underneath it had the tools in libraries. I guess I got some formatting messed up here. In libraries, we had VM core, ASM parser, or the assembly bytecode, this thing called method analysis and optimizations, and some of these things got renamed. Right, AS became LLVM AS, also quite early on. The bytecode became bitcode when we rewrote it all in LLVM 2.0 timeframe. Method analysis eventually figured out that there was nothing really method about it, and again, the Java aspect didn't really pan out, but it's actually a fairly similar structure to what we're I guess stuck with today. The headers that existed were also pretty similar, and so many of the things you see today in LLVM, like value.h, type.h, instruction and instructions, always something that's been weird. Inster types, also weird, but it's a very old problem, I guess. The header file styles actually was quite similar, and if you look at drive types.h, it has exactly the same header file comment, except instead of method, somebody replaced it with function, which is hilarious. Major differences, of course, is that there are some to-dos, like at some point we'll need pointers. But yeah, clear room for improvement there. The makefile system that, again, we're all stuck with, I stole from an earlier project I worked on in C++, and again, it's virtually identical. It's you can kind of see where it came from, perhaps, but it's it kind of worked. One of the more interesting things I thought was that the IR and the concepts of how the SSA system would work were actually pretty well nailed down at that point. And so even core things like replace all uses of with RAR were already in place and were being used, and it kind of falls out of building an SSA-based compiler. And so a lot of things were there. I mean, even the class hierarchy with, again, good and bad decisions of naming and design of how all the pieces fit together were already kind of there and kind of gelled. So I also thought it was kind of interesting to look at the LLVM IR syntax at the time. And at the time, we were talking about Java bytecode a lot, and we were talking about class files. And so very naturally, it seemed that the textual representation should reflect the encoding. And so the very earliest days, you'd have, for example, it's much more efficient to encode small numbers, and so all the operand references were positive and negative numbers to be relative to the current instruction. If you look up, and so you can see the operands here, you can see basic LLVM-like operations. The type system lived on until LLVM 2, I guess, which is the C-style type system with signs in the types and stuff like that. Other weird things, so you can see that the desired syntax was understood but not implemented yet. The other weird things are, for example, there's this notion of a constant pool, something that came from Java class files. There's a class thing at the top. It was very fledgling. Fee nodes didn't actually work. Details, but it was it was kind of going the right way. So we started working on this and picked it up, and the obvious first question you have with the compiler is, okay, well, it's interesting to have a dead code elimination pass, I guess, but how are you going to use it and how are you going to build it? And that was really kind of the turn of the project, because we said, hey, we need to find a compiler, a front end that we could bolt onto this thing so we can actually get real code going through it. And I don't even remember why we didn't end up working with Java, but I read this great paper by Mark Mitchell, and GCC 3.0 was cooking and it was exciting, and so I ended up wiring up a backend for GCC. And very, not in the LLVM 1.0 days, but very early on started working on this, and Learned a lot. Turns out that generating LLVM IR by implementing an RTL backend in GCC and trying to find types later, not a good idea. But I got a lot of experience implementing GCC front ends over the year. Unfortunately, now Dragon Egg has kind of put LLVM GCC out of business, which is a good thing. So it was kind of really interesting. In the early days, we made a lot of progress. We had a lot of fun. At some point, we got more disciplined and decided that, hey, wow, working as a directory of code on your hard drive is not really a good idea. More people wanted to work on it. And so if you fast forward about 6 months, we have version 1 of LLVM. And so you can actually check this out of SVN if you're curious and look at it. And it made a lot of progress in that 6 months. The type system was much farther forward. Have names, have very basic things like that. Vikram had this thing about, it doesn't want to be too C style, and so we briefly we had a fling with Pascal style begin and end. We had a lot of discussion, a lot of debates, and the syntax and design of LLVM made a lot of progress in that time. The contact with other people with good ideas was very, very helpful. You can see, for example, we were thinking a lot about memory and memory optimizations. I think one of the really great things about LLVM is the notion that the IR is always in SSA form. And so if you want non-SSA, you use allocas and use loads and stores. And that's the escape hatch for lots of good things. And that was already in place, again, pretty early on, which I think was a good abstraction. And it just generally kind of started moving this way. Now, arrays were different, and there's definitely problems, but we started making really good progress in building up steam. Again, coming out of these discussions, Vikram and I decided, hey, it might be a good idea to write this down. And so he really pushed for getting langref.html going, which was our first document. We covered many different design topics and discussed this a lot, and a lot of progress was made, clearly. And got some basic, got all the type system in there. SIMD vectors were actually in there for a while and then got ripped out, which was, and then came back as Fortran style vectors, and then those got ripped out, and it turns out that design is hard. We had ideas, I guess, of how invoke was going to be represented and handle exceptions. I don't really remember this, but the code was there, so there's at least some ideas of how this would go in. And a bunch of new optimizations landed, of course. So even things like an inliner, libtransforms IPO, libtransforms scalar, a lot of that basic infrastructure got there. And I think the IR verifier was kind of a really important early thing and supported a lot of bring up. So we spent a lot of time just getting the basics in place. Vikram started working on the code generator, which was a major first thing. 2000, we started implementing a bunch of the core pieces that are now there in LLVM, like the pass managers, mid-level optimizations. Vikram taught a class in 2002. He was very brave. Poor students. This is when the first mailing list came up. You can actually go back in the archive and see them, and kind of just kept charging forward. Even things like bug point came up very, very early on, which was, I don't know, let's just say we had lots of bugs. So it was a very useful tool. Somewhere along the way, I realized that if I didn't write a thesis soon, I never could. So progress halted on the infrastructure stuff, and Vikram was always encouraging me to write papers and not work on infrastructure. But this was one paper I couldn't delay or procrastinate on too long. So it was a lot of fun. We made a lot of forward progress, and leading into 2003, we had our first release, right? And that's what the anniversary is all about. Now, the first release is kind of interesting. You can go, again, download it and look at it. And it had quite a bit of, it wasn't real in many senses, but it had a lot of what makes LLVM LLVM. It had the Spark backend that Vikram wrote, so he and a couple of students, but primarily Vikram, wrote a complete Spark backend from ground up using Berg-style instruction selection and graph culling register allocating and a bunch of stuff. As a side project, a student and I wrote an x86 JIT, and so it was kind of interesting that there was a Spark static compiler and an x86 JIT, which didn't really make any sense. They didn't really share very much code. It was not that great. Had a C backend. Had LLVM GCC bumped up to 3.4, which was, fairly recent from there. And a lot of stuff worked. A lot of the benchmarks were there. The code base had grown. The release notes are kind of funny because the release notes were written assuming there would be more releases. And so it had a what's new section, even though it was the first release and everything was new, which is, pretty hilarious. One of the things we talked about for this release a lot about is what license to use. And the primary thing that motivated us at the time was making sure, or enabling people to use the code. And we really wanted to break down all barriers so that people could use it in different ways, even commercially or in ways we did not want. And particularly when you're coming from academia, there are many good ideas, much good code was written, very little of it actually kind of makes it. And so we were really focused on breaking down barriers, and I think this has been a great decision, looking backwards. Now, 1.0 was great and everything, but of course it had some problems. It was fledgling and still coming of age. Didn't have any vectors, didn't have even complex numbers in the front end, which wasn't really a technical limitation. Exception handling didn't work. Debug info didn't exist. Little details like structs with more than 256 fields completely didn't work because getElementPointer only allowed a byte for the struct index. So there's some really bad ideas. Also, of course, plenty of bugs. And of course, ints-combine hadn't taken over the world and become a library yet. It was only 2,000 lines of code, which doesn't make any sense at all. Now, if you look at it, the IR, looking back, is virtually identical to what we have today. It's actually pretty remarkable. The primary difference is that the types changed. So instead of C-style types, again, we have arbitrary precision integers and stuff like that. You can see, again, getElementPointer with its byte for the struct index, which, tragic idea. There's some minor syntactic things like the % became an @ because of some really bad shadowing problems that, crystalline's namespacing, stuff like that. Also interesting is that the symbol table had, names for every different slice of the symbol table. Maybe some of you old-timers remember this, which meant that you could have two different variables could have the same name if they had different types. Again, tragic idea, but it was quaint. I'm not going to go through all this, but it was actually pretty interesting, even in the 1.0 days. Now, maybe your favorite part, if you've worked on the back end of LLVM, is table gen, right? Table gen was birthed by this. Looking at, so Vikram had been working on Berg for the instruction selector. There's a huge amount of redundancy. And so even if you look back at LLVM 1.0, it had tables for the Spark backend that encoded that had the instruction encoding information. And table gen's all about consuming this data and then puking out code. It really maybe would not have happened if not for Spark's really regular instruction encoding. And so you can blame the guys that designed Spark for table gen. And so it had both backends, and so you could actually see that even way back then, the DAG patterns didn't actually do anything, but they were already starting to be sketched out. So we had a credits file, and one of the interesting things about that is that some of these people are still involved in hacking away. And so it's kind of funny. There was 11 people, many of which were students and kind of came in and did their thing and went out. But some people like Bill and John Criswell, Vikram and Tanya and I are still kicking. So it's been a good trip. So LLVM 3.4 is coming soon. It's 10 years since the first release. It's also 13 years since LLVM was started, which seems like a really long time to be working on it, but I think we're doing some good stuff as a big team. I guess I've learned lots of different things. LLVM 1.0, if you look at it, it had lots of good ideas, but it took a really long time to turn good ideas into something that people could use. And the difference between theory and reality and production quality and all that kind of stuff is a pretty big gap. maybe you guys probably already know this, but LLVM is all about, do something, then make it better, then make it better, then make it better. If you try to make everything perfect from the beginning, you get stuck in analysis paralysis and you don't make progress. And I think that this has actually worked out really well. Mostly because the incremental development has generally happened by people that are smarter than me. And so they throw my stuff away and write new stuff that's much better. And I really appreciate that. Go Raphael for deleting lots of code. Another interesting thing about LLVM is that one of the reasons I really like compilers is I like programming. And you can't, work on, for me, it's very frustrating to work on just the back end. And so I spent a lot of time thinking about Clang, what would become Clang, and I really wanted to work on the front end also. GCC and politics and stuff like that is not really the issue. It's just, I thought that we could do a better front end that would be really awesome. And I was itching to do this for a very, very, very long time. But I think it was good that Clang waited for, 10 years into LLVM's existence, just because the back end needed a lot of work, as you guys know. And if we tried to do everything at once, it probably would not have become good at anything. And I think that LLVM GCC was a good way to go. So the upshot of all this, of course, is that LLVM is a huge project, and you guys are doing lots of work. I know you'd be all very disappointed if I didn't have at least one set of charts. The community is growing really fast, and you guys are really amazing. It's really exciting to see how far and how fast things are going. So thank you all. And I'd like to have Vikram come finish it out.
Let me get my laptop.
You have your laptop?
Okay, so I want to talk about some older stuff and some newer stuff. So the older stuff is a set of ideas that went into LLVM, ideas that had existed before in compilers and in the literature before that, and also some of the early research goals that we had in the project. Chris touched on some of them, like for Java, but there were a few others also. And then the newer stuff is just a little bit about what the impact of those research ideas and the LLVM infrastructure has been through the years, and then where we want to go with it in the future. So looking back, there are a number of major ideas that had existed in the compiler community, both in real-world compilers and in papers, that we had built on and adopted in LLVM. Some of them you probably all are quite familiar with, some of them maybe not so much. One of the biggest ones that you may or may not be aware of came from a paper on the PL8 compiler. This was from IBM by Mark Oslander and Marty Hopkins. And the paper was from 1982, and they talked about this idea called separation of concerns. And the basic concept is sort of straightforward, and many of you probably already are well aware of this, but the basic idea was to separate out the work that each pass does so that each pass focuses on one task and leaves cleanup and other things to other passes in a compiler. But there's actually much more to separation of concerns than just that idea. So they talk about things like flexible reordering of passes, which requires that each pass have the same input format and the same output format, so that you can chain them and reorder them in flexible ways. They talk about having very few corner cases in the compiler so that most passes are exercised on most functions at an appropriate level of optimization. And that makes it just makes sure that each pass is going to be exercised often and it's going to be much more robust. Of course, you have to assume, in order to do things like this, that you have a strong register allocator so that many optimizations can ignore register constraints. You have to assume that you have strong optimizations. In those days, strong meant global optimization. This was across a whole procedure. Interprocedural was not on the horizon at that time. And in fact, they make a strong argument in the paper for why compilers should start using whole procedure optimizations using bit vector data flow. It's actually amusing to read. And if you haven't read this paper, I highly recommend it. I think it has some really strong ideas. These ideas are deeply embedded in the LLVM architecture. And so LLVM really embodies the concepts of separation of concerns. SSA, of course, is widely known. We had the luxury of building in SSA from day one. Many other compilers had to add it as an afterthought and bolt it on. But LLVM is fundamentally SSA based, and we had a number of SSA optimizations from the early days that we could build in. But another one that wasn't an obvious choice is what level of IR to use. So many compilers in those days, including GCC and IBM's and HP and many others, were pretty low-level compilers. They had relatively machine-dependent IRs. And the the motivation was that you could expose much more address arithmetic and things like that to optimizations like redundancy elimination. But it also had many drawbacks. And so, for example, if you think about loop transformations in memory hierarchy and the volume of code, which is has a big impact on interprocedural optimizations, suddenly this low-level representation is not so attractive anymore. On the other extreme, there were compilers like the one at SGI, which had, I think, 5 or 6 levels of IR, and they would successively lower it from one to the next after doing a few optimizations. And that's a complicated design. So what we did in the end was basically pick one really good mid-level IR on which you could do many, many, many optimizations, and then leave appropriate things to the back end. So the machine IR became what it is today. It became basically a way to do machine-specific stuff. And the disadvantage, the cost, is that you have to repeat some optimizations because things like, especially redundancy elimination, which is extremely important on address calculations, couldn't be done on the LLVM IR as effectively. And so now we redo all of those on the machine IR again. But it still works great, and there's not that much redundancy and not that much repetition. Another idea here was the idea of doing cross-module optimization at link time. So there was a paper about this from the HP compiler group in 1988 at PLDI, talking about how it's really convenient to do cross-module optimization by exporting the compiler IR into so-called object files. So they're not really .o files, they happen to contain IR. Link them, do optimization on them, and then do native code generation. And in fact, LLVM has had that since day one. As Chris said, we used the Berg algorithm for our first code generator for Spark. And it's a pretty nice algorithm. It has a number of limitations, and in fact, it got replaced later with the DAG instruction selector. But that was our first instruction selector. And then for our first register allocator was a linear scan register allocator, because in those days, in our heads, we really were thinking about, so actually it wasn't our first. Our first was the graph coloring one we wrote for Spark. But the second one we did was a linear scan register allocator, which a student did, Alkis Lohimenos, Alkis, right? And that was what made it into the x86 JIT as a register allocator. We also had a JIT compiler from the early days. Now, interestingly, we never really did a good adaptive JIT optimizer. We've had a non-adaptive JIT for forever. There's quite a lot of research on adaptive JIT optimization. I think the reason we didn't ever adopt this was because there hasn't really been a production quality system runtime for managed languages. But that might change. There are a number of other ideas that went into LLVM. Obviously, there are many specific algorithms that we've built on, but these are some of the major ideas that are in the design. There were also a number of things that we talked about and decided not to adopt. In the very early days, there was this thing called uncall, which was really more of a hope than a design. It was this hope of doing a completely machine-independent, language-independent format for code. But there was something somewhat more real called ANDF, architecture-neutral distribution format, in the late 80s, and then there was a paper on it in 1991. But ANDF was trying to solve a problem that is actually much harder than it looks, and that problem was portability. So they were trying to develop ways to make object code portable, but object code for arbitrary languages. And the problem is that portability has as much to do with source-level languages as it has to do with object code. And LLVM did not really try to solve this problem. LLVM at least all of it, the mainline LLVM is not intended to be a completely portable format. Obviously, people are now trying to do something that is portable by using subsets of LLVM or restricted versions of LLVM, but with additional restrictions on the languages themselves. So things like what people are doing in Pinnacle and RenderScript and Spear. We looked at the RTL stuff in GCC, and we never even thought about using it for a moment, but it's there. GCC has used it to very effectively. This came out of the University of Virginia. Jack Davidson and Chris Fraser were people who developed it. Bit vector data flow analysis is a more serious omission, I think. So we talked about bit vector data flow analysis. We've never had it really in the system. I think there are some consequences of that. For example, we really don't have a good partial redundancy elimination pass because it doesn't work so well on SSA. We tried. We had SSA PRE for some time, and then it got ripped out. It was much slower, and it doesn't do as well. But for better or worse, we've never had a bit vector data flow analysis. Graph coloring register allocation was there temporarily, but that also went away. But we have very good register allocators now, like PBQP. So it's not clear how much of a price we're paying for not having that. Another big one was compile time interprocedural compilation. So we pretty much committed to doing link time interprocedural stuff from day one. And I think that was a good choice. Compile time has some minor advantages, especially when it comes to source level information. But other than that, link time does really well, and compile time has major engineering problems in integrating with build systems. Adaptive JIT optimization, I already mentioned that earlier. So those are some of the ideas that went in or did not go into the LLVM design. There were also some research goals that we talked about a lot, as Chris said. Dynamic compilation obviously is something he's talked about quite a bit. But we wanted to have a flexible IR for doing dynamic compilation for arbitrary languages, not just Java, but we'd like to do it. We did want to do it for C, C++, and other languages too. And as part of that, we wanted the right division of labor between ahead of time and just-in-time compilation. And so what really came out of that research was not so much a good dynamic optimizer or new ideas in doing adaptive optimization or something like that at runtime, but the idea of doing lifelong compilation, being able to do program transformations at compile time, at link time, at install time, at load time, or at runtime. And even at what we called idle time, which is between executions on the end user's machine. And LLVM does enable all of these things to be possible. So that was really, I think, the major outcome of the dynamic compilation side as far as the research was concerned. And then a second thing that we wanted to do was to provide a set of language-independent services so that you could build implementations of many different languages from a common toolkit, which would consist of not only machine-independent optimizations and code generation, language-independent optimizations and code generation and things like that, but also a JIT management framework so you could build JITs for arbitrary languages, exception handling, garbage collection. All of these things would come as common services in a common infrastructure. A third direction that Chris mentioned also is memory hierarchy optimization. And by the way, this was actually the topic of Chris's PhD thesis. I think it was called macroscopic data structure optimization, right? And the idea was, could you recognize data structures, recursive data structures, pointer-based data structures, and distinguish them in a compiler using a pointer analysis? And if you did that, then could you control the layout of those data structures? And so that became data structure analysis, which is a pointer analysis, and that appeared in PLDI 2007 after Chris graduated, by the way. We had another student, Andrew Lenhardt, who wrote that last version of the paper. I think it was like the 5th version or 6th version or something. But it finally got into PLDI. And Andrew presented it because Chris couldn't be there. But then we also had this paper on automatic pool allocation, which was talking about how you could control the layout of data structures after you'd identified them using the pointer analysis. And that appeared in PLDI in 2005 and actually won a Best Paper Award. So those were Chris's PhD thesis topics. But in reality, I think the first two directions had a lot more real impact. And so, for example, lifelong compilation has been used by many, many different real-world products. So on the left here, I've listed some of the major commercial products that use LLVM, and you can see that many of them have taken advantage of doing compilation at multiple stages. So, for example, RenderScript does both compile time and either runtime or load time compilation and transformation. And there have been many, many research projects that have taken advantage of being able to compile things at different points in time. Language-independent services have been used to build language implementations in a really remarkable range of different languages. In fact, I don't myself know of another infrastructure that has been used for such a diverse set of languages. If you know of one, I'd be interested to hear of it. But we've done static languages, managed languages, scripting languages, explicitly parallel languages. Not all of these are production quality. In fact, many of these are experimental. But there are real implementations that work for reasonable subsets of the languages. And some of these, of course, are production quality. The other way to look at the impact is to look at the range of different systems that have used LLVM. And this spans all the way down from the little microcontroller at the end of your Thunderbolt cable, or Apple's Thunderbolt cable at least, all the way up to large supercomputers like the Blue Waters at Illinois, which is one of the largest academic supercomputers in the world. And many, many things in between, including mobile devices, iOS, Android, tablets, desktops, and everything else. In fact, I think in practice, only GCC has had a comparable, or in fact, even broader reach. GCC is in many, many embedded systems that LLVM doesn't get used for. But it's really mainly for static languages. So GCC doesn't do the range of different languages that LLVM is able to support on many of these systems. It's quite a combination. Another somewhat amusing take on this was an article that appeared in Wired in July. Did you know that LLVM is the last remaining connection between Apple and Google? I didn't know that. But this, so I think this was sort of a teaser to get people excited about reading the article. If they had said something like LLVM is a really powerful software system or compiler system, LLVM is used by many software projects or something else, I doubt that more than a small fraction of their readers would even care. But the article actually is quite interesting, and it has lots of good insights. It's a valuable, it's a worthwhile article to read if you haven't read it yet. In fact, somebody told me the only thing better than a love letter from Wired is a long love letter from Wired. And I think there's some truth to that. It really is quite a glowing article. I also wanted to show off a little bit. I think this is something that we don't often do, but it's worth noting. There are a number of things that LLVM has done that have not been done before or been done better than ever before. It was the first production JIT compiler for C-based languages that I know of. So this was in the first commercial product using LLVM, which was Mac OS, which was the OpenGL stack in Mac OS, which used LLVM as a JIT. Clang and LLVM have fully replaced GCC in Xcode 5, and so Apple is now fully a Clang shop. It used to be a fully GCC shop. It's used in both major mobile platforms, iOS and Android, and that's pretty uncommon. It's used for most GPU compute languages. So all implementations of OpenCL that I know of, CUDA, RenderScript, all use LLVM. It has the first complete C++ 11x language and library implementation, which is also a nice first. It's not easy to do that, obviously, because C++ is an enormous language. And the first ARM64 compiler in production. And we got some nice awards along the way. I think this is also worth touting. In 2010, Chris won, so I nominated Chris, and he won the SIGPlan Programming Languages Software Award, and the citation for that says LLVM has had a dramatic impact on our field. And you have to remember, this is given by researchers mainly. So they talked about significant influence on academic research, not just in compilers, but also in other areas. I think a much bigger and more important award was given by all of ACM, which is the ACM Software System Award, which is given to one system worldwide. And the winners list is just breathtaking. It's quite amazing, the list of things that are on there. But even some of the recent winners are quite interesting. And then Chris won the Computer Science Distinguished Alumni Achievement Award this year for all of his work on LLVM. So there's lots more to come, and these are my last couple of slides. There are a number of functional improvements that are coming down the pike or will be coming down the pike in the near future. More complete Windows support is a really big one. There are many people asking for this. More effective profile guided optimization. We'll actually hear more about this in a talk later today. Improved usability and much better speed for LTO, including being able to run LTO in parallel, which is difficult. It's not straightforward to do that. Improved auto-vectorization support. It's already gotten really good over the last 1 year, but it can get better. Improved debugging support, and a big one that has been missing for a long time, which is state-of-the-art pointer analysis. Those were improvements in some sense to the existing system based on ideas that already exist and in domains that it's already used for. But there are also new areas where LLVM is not used and where it really could be. And these are essentially any place that compiler technology is used today. So, for example, JavaScript in web browsers is a really big target, and I'm told that there is an implementation of JavaScript coming out that will be production quality that uses LLVM as a JIT. So watch out for that. And then a second one is just managed languages. There is Mono for .NET, which is used on some systems, but Java is pretty much a big hole. Most people use Hotspot and other commercial systems or JIX RVM for research. And that's a really big missing one. Linux kernels and derivatives mostly don't get compiled with LLVM today. In production, Linux doesn't at least. But Android and Chrome OS are both being brought up using Clang and LLVM. And that's going to be a big change if it comes about. So FreeBSD and macOS obviously already are compiled that way today. Embedded systems, I think, are a very large domain where GCC it's a stronghold of GCC. LLVM has some significant advantages, the same kinds of things in the desktops, but code size and there are a number of other issues that have not been a major focus for LLVM so far, which I think will help a lot here. And then heterogeneous computing, especially SoCs and mobile devices, is an area where I think it's ripe for a better representation. And more IDEs. So Xcode really works well for Mac, people building on Macs. But Eclipse and Visual Studio and all the other IDEs out there don't have any LLVM integration. So I admit some of these might sound a little far-fetched. They might take a long time. But I think that it's worth thinking about them and working on them. 10 years ago, who would have thought LLVM would completely replace GCC at Apple? Our hope was that there would be a few commercial users and as many research users as we could arm twist into using it. It's grown far beyond anything that I think we would have dreamed. So that's all I have to say. Okay.
Thank you, Vikram and Chris. Now we're going to move to the next talk, but for those who want to go to the other rooms, now is your opportunity. We have the code size reduction talk in Mercantile, and there is a BOF in Currency. Like I said, just exit the doors, go to the left, into the hotel, down to level B. And we'll begin in about 3 minutes for this talk to give people time to transition. Thank you.